Hi, everyone. My name is Brian Munoz. I'm the program director here at WIDS Worldwide, Women in Data Science. We were launched as an initiative out of Stanford University in 2015. And today we're going to be hosting a workshop on causal inference in business presented by Shreya. That being said, I'm going to hand it over to Shreya so she can introduce herself and go through her presentation. Thank you for joining us.
Of course. Hi, Brian. Thanks for the intro there. Hello, everyone. I'm Shreya. I'm a staff data scientist at Walmart. I am primarily a statistical and a causal influence modeler. And for the last one-ish year at Walmart, I have been working on a wide variety of statistical model, econometric model, and fixed effect causal models, and that has primarily been my career. I have spent about a decade now in the industry. Feels like a long time, and during the entire time, I was, mostly working on econometrics based models and sometimes, machine learning models. With that being said, let me quickly jump into the presentation and start with some value addition for this presentation. So this presentation is primarily aimed towards individuals who are interested in this domain. So if you are somebody who want to know about the underlying theory of causal inference model, or in general an econometric model, how it works and how one can use a causal inference model for doing impact evaluation, then this is the right lecture for you. And this is also a very good presentation that can be used by folks who are preparing for interviews for product analytics roles, data science roles, or economist roles, because in most of these roles, particularly in the tech industry, people are required to do impact evaluation, because the tech industry is launching a wide variety of products, features, campaigns, etc. And they need a proper, scientifically accurate evaluation and attribution of revenue towards all these initiatives that they take. And that is why they require their analysts to do something that is scientifically backed, and also something that is repeatable and reproducible across various kinds of the data set. So during interviews, the interviewers expect the candidates to know the theoretical core justifications of how these models work. They require people to be able to do this from scratch without using any of the packages. So that is why I feel this is going to be a very valuable presentation for you if you are planning to interview in the analytics and economics space in any of the tech industry. With that in mind, let me jump into the presentation. So this is going to be a fairly technical presentation. It will involve some degree of mathematics and mathematical expression. So I am going to do a quick refresher, but that is for people who are already familiar with some of the core concepts. I would expect that the audience is familiar with basic undergraduate statistics, basic undergraduate econometrics. They know what is a statistical distribution, what is a random variable, what do random variable mean, what is variation, and some basic properties of a distribution, which is mean and variance. I would also expect that the audience is familiar with concepts like hypothesis testing, confidence interval, p-values, t-test, and all this, and how to do inference from a data set. And I wouldn't have time to go over these concepts. So if someone is not familiar with these concepts, it's highly recommended that the audience get themselves familiarized with these concepts before going further into this lecture. I'll be using some basic notations throughout this course. So those are the notations for expectation, which is like a big capital E. It is used to calculate average for a random variable. I'll be using the notations for standard error, and I'll be using subscripts and superscripts to denote behavior of various entities that will be captured in a regression equation. So I would highly recommend the audience to be, familiar with these notations and, the expression of a basic linear regression before, they go further into the presentation. With that in mind, let me talk about background and context. Where do we use causal models? So, causal models are typically used in two types of scenarios. One is a randomized experiment. So, where another word for randomized experiment is an A/B test. So, it typically means a situation where the analyst has a lot of control over the experiment. They can determine how the experiment will roll out, who will be exposed to the treatment and who won't be, and how will that exposure happen. They are able to collect data on the subjects of the experiment before the experiment has happened, and they also have collected data after the experiment has happened. So this is typically a setup where randomized experiments are typically used. Now, oftentimes, randomization is not possible. Sometimes randomization is not possible because product managers don't really think that they can do randomization. They need to do a quick they have a quick go to market strategy, and they need to roll it out very fast. They don't have the time to experiment and figure out marginal impact before going to the market full scale. Sometimes, because of engineering constraints, randomization is not possible. Sometimes, like the experiment has already happened, and all that we have is historical data to evaluate the impact of that event. There can be a wide variety of situations where randomization is not possible. So in those situations, typically causal models are used. uh, that is mostly the background. And another area where causal models are widely used are policy spaces and lawmaking spaces. So oftentimes there are all these social policies. For example, giving out scholarships to students, or in developing countries there are programs like giving out mosquito nets to certain members of the village. So typically in these type of situations, whosoever is analyzing the impact of these programs don't really have a lot of control over how the program will happen. And in those type of situations, people are often tasked to do the impact evaluation after the treatment has happened, and in those situations too, causal models are widely used. I hope this clears and gives the audience a little bit of idea about, when and why causal models are used. And then I'll just, quickly do a basic econometric refresher. So I'll be a little fast when I'll, talk about these refreshers, because I would assume that the audience already knows this is just for me to refresh somebody's memory. These are, some of the concepts I'll be covering in the refresher. So I'll start with the linear regression, which is the fundamental tool that we'll be using, and that is still used in the industry. The most widely used and the most popular causal models still use a linear approximation of the nonlinear forces that govern the impact evaluation. And oftentimes what we have seen is a linear regression is a very good approximation of the nonlinear forces that are at play. So that is why we are primarily going to be focusing on a linear regression. And linear regression has two basic components. One is the dependent variable, which is the y. It's also known as the target or the outcome. The second one is the independent variable, or the vector of covariates that I'm going to be using. This is also known as features in the machine learning world. Now I have a data set of various entities. These range from 0 to n, which means I have n rows in the data, and each row represents each individual who are a part of my experiment. And then I have k independent variables or features that are measured. So for each of those n rows, I have one column for the target, and then I have 1 to k columns representing the features that control the target. So I actually have an n into k matrix over here. And the purpose of this linear regression is to explain variation in y. So what do we mean by variation in y? I have data on the target for each row, right? So the value of y for each individual is a little bit different. For some, it's very high, assuming it's a continuous variable, and for some, it's low. And there is a variation in y across individuals. And we are trying to use this linear regression to explain this variation, this different behavior of y across different individuals. We want to know how can we use this vector of x's to explain that variation in y. So if you really look at the variation in y, there are some systemic components that are controlled by all these x's over here. And then there is an idiosyncratic or a random component, which is represented by ei. And what it means is that there is some degree of fluctuation in yi across various members of the population that cannot be explained by anything that is measurable or that is there in my data. And that variation is accounted for by a random term or a random noise, which is the ei. And because of this random noise, this system of equation is a stochastic equation and it's not a deterministic equation. So that's why we don't take average of like a simple average of y. We have to take expected value of y, which is the statistical way to measure average for a random variable. Now let me explain this by using an example. Suppose I am trying to explain why different members of the population have different salary or wage. And let's suppose I have two variables, years of education and gender. Both of different members of the population have different years of education. This is a continuous variable and they are either a man or a woman. So I have a 0 or 1 indicator for gender. Now, how to interpret these coefficient estimates? So let me start with this beta. So the beta is basically determines my average salary if I have 0 years of education and if I'm a man. So what it basically means is that let's suppose that uh, I am dealing with people that have 0 years of education. That is people who are illiterate. Then what beta would tell me is the average difference in salary between people who are men versus people who are women. So this beta 2, if this is positive, then I would say among illiterate men and women, women have higher salary on an average over men. And if this beta 2 is negative, then I'll say that among illiterate men and women, women will always have a lower salary compared to men. And the way to or interpret beta 1 is how years of education impact my salary. So another extra year of education will increase the salary by beta $1. So that is how one should interpret beta 1. And of course, there is a concept called statistical significance. So what it means is that if the p-value associated with these coefficient estimates, if they are greater than let's say 0.5, 0.05, then we can say with confidence that this coefficient estimate is significantly different from 0. Again, I'm not going into the detail of p-value. I'm assuming that the reader is familiar with it. But this is basically how we use the results coming from a regression like this. I have a graph over here to explain it a little bit better. So let's like the notations are slightly different, but the overall meaning is the same. I have, salary or wage as my outcome, and I have like a 0 1 indicator for gender and another continuous variable for, years of education. So the slope of this graph is controlled by the beta 1. So as you see, if the slope is positive, that is if beta 1 is positive, then we can see that another year of education would increase the salary of both men and women. But if you look at the intercept where years of education is equal to 0, and we are assuming that delta naught is negative, then that means is that among illiterate men and women, men will always get a higher wage compared to women. Beta naught will always be higher than beta naught plus delta naught, which is negative here. And now, as we, give them higher and higher education, both of them will, start getting higher wage, but the basic difference in wage between men and women will continue to persist. And this is how one can use and interpret and get value out of a coefficient estimate of a linear regression. With that in mind, let me quickly talk about some basic assumptions of a linear regression. So, a linear regression can provide meaningful statistical estimation if certain assumptions hold in the data. If these assumptions don't hold, then we have to make some adjustments to the linear model. Again, I'm not going into it, it's a very different area altogether. The one assumption that I will like to put forward to everybody is normality of the error terms. So what this means is that the error term or the random error in our distribution, if I measure it across various samples, it will have a normal distribution with zero mean and constant variance. So what that means is the error is basically what I'm not able to estimate using the data. So yi, which is my actual target, and the estimated yi is what I was able to estimate using the data, and the gap between the two is basically what is my error term or the random component between the actual value and the estimated value that I couldn't evaluate from the data. Now, for some individuals in my data, the actual value would be higher than the estimated value. For some individuals in the data, the actual y would be lower than the estimated y. So for some individuals of the population, I will overestimate the y. For some individuals in the population, I will slightly underestimate the y. But if I take the average of all the individuals across the population, the average will be 0. If my linear model is working, then my average should be 0. And if I consider or if I take this average across various samples, then I'll get a normal distribution which has a center around 0. And that is the most important assumption that we need in a linear model in order to get uh, statistical hypothesis testing from the model. We need this in order to use p-values in a meaningful way. And if we don't have this, then one can do various transformations in the target to get this back. Okay, the other important concept is standard error. What is standard error? So standard error is what makes my coefficient estimates robust. So I will get, let's say I have one data set, and if I estimate the linear regression on that data set, I will get a particular value of beta. Let's say if I estimate the same linear regression on another data set, I will get another beta. But these two betas or any other beta that I will get from any other sample shouldn't be very different from each other. They should not fluctuate a lot. And that is what is given out by the standard error. And this standard error is used to measure the confidence interval. So it is always important whenever we see a coefficient estimate, we also see and evaluate its standard error closely and make sure that the standard errors are low. Otherwise, we will not be able to take the beta coefficient seriously. If it's too big, that means it's not robust. It's volatile and it will vary across various data sets. So it's basically not reproducible and generalizable. And that's why the value of the beta is not really very meaningful for us. Now, another concept of linear regression is very important, particularly in the context of causal models, that is dummy variable. So, how do dummy variables work? So, I'll again explain this by using a simple example. Let's suppose y is my salary, and I'm trying to explain why by using only one dummy variable, which is gender. So it will take a value 1 if the individual is a woman, and it will take a value 0 if the individual is a man. And I have a regression equation like this. Now, what is beta 0? Beta 0 is the average salary for men. So if x0 equals xi equals 0, which means I'm only looking at the men, and if I take, then my equation will look like this. Sorry, my equation will look like this. And then if I take an average, since expectation of this EI is equal to 0 based on the assumptions of the linear model, I will only get beta 0. And then what if I look at only at the women, which means if xi equals 1, then my model will look like this: beta 0 plus beta 1 plus epsilon I. Now if I look at if I take an average of this y, which is the expectation of y given xi equals 1, I will get beta 0 plus beta 1 because expectation of ei is 0. Now if you look at this term and this term, then you will be able to see by moving a few terms here and there, my beta 1 is equal to the expected value of y given x equal to 1 minus expected value of y given x equal to 0. That is, my beta 1 is simply the difference in average salary between women and men. And that is how one can interpret beta. It is, if xi is a dummy variable, then the way to interpret my beta associated with that dummy variable is the difference in y across the two groups of population captured by this x. And this is a very critical piece of information that is going to be repeatedly used in the causal models that I'm going to be covering later. So I would request you to store this information at a corner of your mind such that when I need it, we should be able to refer to it. Okay, and here is like a simple situation where I have taken like a very simple data set to, demonstrate this. In the interest of time, I'll skip it. And then I am going to come to the very base content of this exercise, that is, what is causal modeling. So, causal modeling is a way to do impact evaluation. So, I'm trying to get the impact of something on someone. That is essentially what we are trying to do. We are trying to attribute some quantitative number to a particular event that has happened to a particular group of population to evaluate what was the benefit of this event. Now let's suppose we have data on two groups of people. Let's take an example. Let's assume that we have two groups of people. One group of people who have visited the hospital in the last 30 days and another group of people who did not visit the hospital in the last 30 days. Now suppose we have one data on one outcome, the overall health status of an individual. It's 1 if it's good and it's 0 if it's bad. And now the task associated with this example is to answer this question: does hospital visit make people less sick? Right? Seems like something very, very, simple. So what one can do is one can do a naive approach, right? You look at the people who visited the hospital, you look at their average health status, and you look at the average health status of the people who didn't visit the hospital, and then you just do a simple subtraction. Just average y of people who visited hospital minus average y of people who did not visit the hospital, right? Seems very intuitive. So, in many studies, this has actually been done, and the result that is seen is that people who had a hospital visit have a lower or a poorer health status compared to the people who didn't do a hospital visit. So, now, it's a puzzling result, right? So, does that mean that hospitals make people sick? Does that mean that, we should stop going to hospitals, or cities should stop, running hospitals, right? Somewhere, something doesn't add up. It cannot be the case that hospitals are detrimental to public health. It cannot be the case, right? So, what were we missing here? So, the reason why we got this type of a puzzling exercise is because in our study there is a selection bias. And causal inference helps in measurement of the selection bias. And that is why we have causal models. That's like one very plain, simple observation. Now, what is the selection bias for our use case? So, people who visit the hospital are sicker to begin with. And let's say that we are trying to get the impact of hospital visit on overall health status after the hospital visit, right? How hospital visit is connected to overall health status. Now there is this confounder that we did not really include in our naive approach. That is the initial health status of the people visiting the hospital. So, sicker people are more likely to visit hospitals, and sicker, like people who are sick now, are likely to be sick in the future too, or likely to have a poor health outcome in the future too. So, I have this confounder over here that is impacting both of these variables. And that is the reason why we are getting that type of very confounding results, because we are effectively looking at very or comparing very different types of people, healthy people with sick people, and we are like inherently healthy people with inherently sick people, and we are trying to compare their health status. It's not an apple to apple comparison to begin with. And that's what causal inference helps us with. It helps us to systematically remove selection bias. It helps us to do an apple to apple fair comparison. And that is essentially what we'll be focusing on for the rest of the presentation. I hope you have some intuition now with respect to what we are trying to do. And with that in mind, let me go to a more formal derivation of what is known as a potential outcome framework, or a Neumann-Rubin potential outcome framework. So we have some entities in this framework. Let me, talk about them. So we have, you know, treatment variable represented by di. Now this variable di, it is a dummy variable. It can take a value 1 if the individual I receives treatment. It will take a value 0 if individual I does not receive treatment. And we have two potential scenarios. So that is the outcome if individual I receives treatment, the outcome if individual I does not receive treatment. And the question that we are tasked with answering is, does D cause Y? Very simple question. I have values of D and I need to know whether D cause Y. Now, what's a very simple answer? The simple answer is take the subtraction yi1 minus yi0, right? Only I wish if we could. Then that's because we don't have data for individual I for both of the scenarios. The individual eye, if it receives treatment, then I can't really observe what the individual's outcome would be if he had not received treatment. We cannot really, you know, look at the potential outcome for individual eye under both scenarios. We cannot observe individual eye in two alternate universes. So effectively, we are dealing with a missing data problem. Let me use this information, this table to illustrate it. So let's say that I have individual observations on 8 individuals and I have information on their treatment status. The first 4 of them were exposed to treatment and the next 4 of them did not get exposed to treatment. So this region highlighted in the red box basically shows what data I would like to have. So I would like to have data on both these columns. Outcome if I receive treatment, outcome if I did not receive treatment. And what I have is for the treated population, the outcome in the universe when they receive treatment, and then in the control population, I have outcome for the universe when they did not receive treatment. I cannot have, data on these two. And hence, what we have to work with is what is known as observed Y, which is the outcome from one of the universes in which we have collected the data. And we have to work with this. And this is the crux of what we deal with in causal inference modeling. We deal with observed Y. We do not really have data on potential Y. Now, let me quickly talk about some terminologies that I'll be heavily using. So, I think by now you are familiar with treatment and outcome. Let me start from estimand. Estimand is the quantity that I'm trying to estimate. It can be the average health status of individuals. It can be purchase in an e-commerce website. It can be a student score of in a school after they have received a scholarship. It can be a wide variety of things. So the conceptual element is known as estimate, and estimate is the actual value of that estimate that we get from the data. And estimator is the method or the formula that we are arriving to get a value for the estimand. So let's suppose that I want to measure the outcome of, hospital visits on the health status of people. So my estimand is going to be, estimand is going to be the overall health status. Estimator is going to be whatever causal model that I will use, and estimate is the actual value that I came up with after using the causal model. The next 3 terms that are also very important and I'm going to be using it very frequently are ATE, average treatment effect, ATT, average treatment effect on treated, and CATE, conditional treatment effect. So average treatment effect is what we would try to evaluate. Average treatment effect is what most causal models try to evaluate. Average treatment effect is the average value of this column. I look at the whole population, the treatment and the control population, and I take the average of the observed Y in the treated population. I take the average of the observed Y in control population, and then I try to understand what is the impact of my treatment in the difference of like these two averages. This is known as ATE, and this is what the causal models all over the world are trying to measure. Now there is something else called ATT. That basically means if I only look at the treated population, what is the impact of my treatment? So sometimes, it is not possible for us to look at the control population. For example, in the e-commerce website, it, let's say for, whatever reason, treatment was given out to avoid, majority of the people who log in. So in that situation, my control group are people who do not log in. Now, I don't have data on those people, right? Who do not log in. So now all I have is the treated population or people who were exposed to treatment. So can I then just do or take their average value before the treatment and after the treatment and take the subtraction of the two and give that out as the impact of my treatment, whatever it was? Can I do that? The answer is in some situations I can do that. And that is what I'm going to be explaining later on. And there is another last concept called CATE, or the impact of the treatment on certain groups of the population. So ATE on certain groups of the population. So, for example, let's say I want to see the impact of a targeted ad program on men versus women. I only, let's say that, ads went out to all users. Some of them were men and some of them were women. Now, let's say for some reason, I believe women respond to the targeted ads more than men. So if that's my belief, then I would like to measure the ATE only on the women. So, what was the impact of my treatment on the women population? So, in those situations, what I'll end up calculating is not the ATE but the CATE. So, with that definitions in mind, let me talk about the theoretical framework and how mathematically we would express these three, concepts. So this is a formal derivation of the Niemann-Rubin causal model. So this is not like some fancy calculation. It is just, simple mathematics. So think of DI as like an on and off switch. So it will take a value 1 if treatment has happened. It will take a value 0 if the treatment has not happened. And if individual I got exposed to treatment, his value is yi1. And if the individual did not get exposed to treatment, his value of y would be yi0. So, treated population, di equals 1, then this whole thing will go away. Then my observed y will be equal to yi1. And if di equals 0, then this entire term will go away. This will become 1. And my observed y will be equal to yi0. Now my ATE, this is for the individual. Now I cannot really, have data on yi1 and yi0, right? Because I can observe an individual in only one of the scenarios. So what I do is ATE. I look at the observed y and take this tau I is the observed y. This tau I is basically this. Each element, like, tau 1 is this, tau 2 is this, tau 3 is this. So the tower is, individual observed y. I will take the average across all the population. So it is the expected value of yi1 minus yi0, and then I can split the expectation. And my ATT is when I have a condition. The same thing, but only on the treated population. And Kate is again, it is ATE with another condition, some subset of the population, X equals X. It could be gender equals woman or any condition. And in some situations, we might be interested to measure Kate. I'm not going to cover Kate in this, solution. In this lecture, it's a part of heterogeneous treatment effect, which is again, it deserves another lecture on its own. Okay, so I hope now the intuition, both theoretical and mathematical between ATE, ATT, and CAT is clear. With that in mind, I am going to talk about, some mathematical expression of selection bias and why selection bias is important. So you see how to express ATE. So ATE is the expected value of y between the treated and the control population. Now I can do some algebraic trick. I can break it up in this way. The the average or the expected value of the yi post treatment minus pre treatment, pre versus post among the treated population. And I can also write this, like include another term here, the expected value of y between treated and control population pre treatment. You can see these two terms will cancel out. Then this term and this term, the first term and the last term, is exactly the same as the ATE, the original equation here. But now if you look at it a little bit carefully, and you can use the formula here to make comparison, this term over here is my ATT, or the the expected value of my target pre and post treatment among the treated population. And the second term is the selection bias, which is in the pre treatment period, what was the average value of y. So for the hospital visit example, if in the pre treatment period, people in the treated population are sicker to begin with, this value is going to be higher than this value, and selection bias would be non-zero. But if we are dealing with an e-commerce example of targeted ads, where ads were targeted randomly, then the selection bias will be zero. Then my ATE will be equal to ATT. So, long story short, selection bias is important because selection bias is what distinguishes between the average treatment effect and the treatment effect on the treated. And in the absence of selection bias, we can just measure ATT and we can go ahead with it. But if we want to measure like a proper causal model, and if we have a suspicion that there is selection bias, then we have to do a proper measurement of ATE. We cannot really do the pre and post subtraction of the outcome in the treated population. And that is basically the summary of selection bias and why selection bias is important. Okay, there is another thing that the user needs to have in mind, the audience needs to have in mind. That is, when is ATE identifiable? So what is identifiable? Identifiable is when can I measure the treatment effect from the data. So the data needs to satisfy certain assumptions in order for it to give me a reliable estimate of the treatment effect. So there are three major assumptions. So these assumptions are, the first important assumption is Sudva, which means no network effect or externality. That is, if individual I receives treatment, that reception shouldn't impact the probability of individual J's receiving treatment. So what I mean, let's say that if you log into an e-commerce website from your home, the probability of you seeing an ad should not impact your neighbor's probability of seeing the ad if he logs in from his home at the same time, right? So you and your neighbor should be independent, like you logging into the ecom website and your neighbor logging into the ecom website should be independent events, and the two should not be related to each other. Now it seems obvious that this should always work, but there are many situations where it doesn't work. Let me give you an example. For example, let's say for ride sharing services like Uber or Lyft, let's say that the treatment is something like search price. So, in Uber, you see a search price if there is a lot of traffic in your area. So, let's suppose two of your neighbors have already used Uber to book a particular ride. Then Uber system would think there is more traffic in the area, and when you will be the third person who will log into Uber from the same locality or exact same geographical location, you are very likely to see the search price. Whereas if your neighbors didn't log in and request for a ride at that exact same time, you will not you will not have been exposed to the treatment of getting a search price. So there are all these applications in, in booking service, booking websites like Airbnb or hotel.com, or these ride sharing services like Lyft and Uber, where this no network effect assumption is violated. And in those situations, they do not do individual level randomization. I won't be covering the, this use case in detail, but this is like a key assumption that needs to hold for a causal model. Now, the next two assumptions are strong ignorability and equal treatment probability. Strong ignorability is nothing but no selection bias. So, at the time of the treatment assignment, treatment is not assigned in a way where people who are getting treatment are more likely to give or to generate a positive outcome. It should not, the treatment should not be meted out in that way, which means potential outcome between the treatment and the control population should be independent of, DI, given XI or all other covariates that impact Y. So for example, let's say in a school, right, I'm giving out scholarships to, students. It should not happen that the scholarships are given out to students who have a better grade and better IQ. Then I am selectively picking people who are likely to do better in their studies anyways. So the impact, if I look at the, student score post the scholarship, if I see a higher, performance, then I don't know if this higher performance is coming from the scholarship or the fact that these students were smarter to begin with. So that is known as strong ignorability. And the last assumption is equal treatment probability. What that means is that every individual should have an some positive probability of receiving treatment. It cannot be the case that there is one individual in the population who would never receive treatment. For example, there is, let's say, in school, there is one student who belongs to a certain race which would automatically disqualify the student from receiving the scholarship. If that type of situation exists, then this assumption would be violated. So we have three of these assumptions, and as you can see very well, when treatment is given out randomly, both the second and the third assumptions, strong ignorability and equal treatment probability, will always hold. So that is the reason why most people prefer to do a random treatment assignment, and random treatment assignment is like the gold standard in the industry. Now, what will happen if, I mean, okay, last statement. How do we measure a causal model using an econometric setup? So if the treatment is randomly assigned, we can estimate the impact of the treatment by the first equation here. So this TI is a random, it's a dummy variable. It will take a value 1 if the individual belongs to the treatment group, and it will take a value 0 if the individual belongs to the control group. And this is the point where I would like you to remember what I told you a couple of slides back on dummy variable, how to use the coefficient estimate of the dummy variable. So as I have already explained over there, you can use this beta, or this beta is equal to the expected value of the y between the treated and the control population, which is why this works to estimate ATE when the treatment is randomly assigned. Now, what happens if the treatment is non-randomly assigned? What you have to do is you have to use all the sources of selection bias in your model. All that goes into this xi, or the covariate vector. Everything else that are confounders need to be there in this, vector. And that is oftentimes a problem because this vector can be huge. There is a dimensionality problem, like, we can have 500 variables there, then the model will suffer from, like multicollinearity problem or dimension problem. The other problem that we might have is measurability problem or availability problem. There might be some x's that are not even available, we don't even have them in the data. So for both these situations, you will see that, you know, using this equation or estimating this equation is not feasible. And that is the reason why we have causal models, because this equation, although it looks simple, it's often not, feasible in practice. So what do we do? And before I get there, I have, one slide which I believe is very important, is when is ATE non-identifiable? When can we not, have a reliable measure of ATE? That is when there is an unobserved selection bias. What it means is that, let's suppose that I have a UI or some variable that is not available. But I know if it were available, then we would have an equation like this, which is that the expected value of the ATE is typically higher for people having, let's say, a value 1 for the UI, and it is, lower for the people having a 0 value for this UI, and UI is unobservable. In that case, I will have an unobserved selection bias problem in my model, and then the ATE would be unidentifiable. And a classic example of it is the impact of ad targeting campaigns on customer purchase. So customer who are highly engaged and highly interested in the product typically browses the product more, and they are the people who get, targeted with ads, and these people are very passionate towards these products, so they will very likely buy the product. So if you measure the impact of those targeted ad campaigns on customer purchase without really incorporating this unobserved factor in your model, then your estimates will suffer from a bias. It can be biased upwards, it can be biased low downwards, but it's most likely it's going to be, biased upwards, which basically means that, the estimate that you will evaluate, it's going to be higher than what it is in reality. So the impact that you will quote to the leadership is not the true impact, it is a biased impact, and it's overestimated. The true impact is actually lower. And that is why having a proper causal model is very important, because the leadership of a company needs to know that, like whatever impact you are quoting to them, it's not inflated, or it's not like, over measured, or like, it's not overestimated. They need to allocate their revenue or their resources towards the right program that is actually, leading to marginal revenue generation, not, inflated revenue numbers. And that's why most of the big tech companies care about causal models in a very important way. Now let's come back to our problem. Let's In this lecture I will cover two of the most widely used causal models in the industry. One is difference and difference, and one is propensity score. So difference and difference, or two-way fixed effect estimator, is a way to take care of or tackle this unobserved selection bias. So let's suppose that I have selection bias. Then what do we do? Do we not do causal evaluation at all? Is that the best that we can do? No, right? So we can still come up with a stable and trustable and unbiased estimate. How do we do that? Can do that if the selection bias is time invariant. That is, whatever is the selection bias, it is different for different individuals, but it doesn't vary over time. Why can we do it? We can do it because of the typical algebraic manipulation that difference and difference offers. So let's go into it in further details. So I have a treatment variable, and another very important example, like, point to note down is difference and difference can be used when the treatment is typically implemented at a group level. It may or may not be random, but it is implemented on a group. Like certain villages got exposed to the treatment, certain villages didn't. Certain cities, or like certain product hierarchies in an e-com website got exposed to the treatment versus, like, we did it only for electronics but not for, consumables. So the treatment should be implemented at a group level, and now my data and the treatment implementation is correlated with the group characteristics, which is like, it's implemented on a group of, let's say, individuals, or like a group where, like, typical purchase and consumer engagement is high, or something like that. The selection bias also exists at a group level, and I have data on a individual level. That is where we use two-way fixed effect estimator. Now we need we need panel data. That is, we need data at an individual level. So for one individual, we need to observe this individual over multiple periods of time, a good number of, time periods before the treatment has happened, and another good number of time periods after the treatment has happened. Now, is that enough? No, we need more for, this model to be effectively used. The next are three very important sets of assumptions. So our data needs to satisfy these assumptions for us to use this method to generate an unbiased estimate of the treatment. So the first and the most important assumption is parallel treatment, or parallel evolution of the outcome, or parallel trends. What it means is that it is okay if the selection bias happens. So let me actually use an example to, quote it. For example, let's say, one situation where you could use a two-way fixed effect estimator is when we are trying to evaluate the impact of providing mosquito nets in villages on the overall incidence of malaria. And now let's suppose that we have given the treatment to, let's say, villages in a certain district, and we have not given mosquito nets to villages in another district. It might happen that the policy has given out mosquito nets to, districts that have, let's say, more villages that have a marshy area, which means that, like, these are the areas where mosquitoes grow more, and people in this, districts have higher malaria, due to which, mosquito nets were given out to them to get the maximum possible, impact. But that would not, let us, I mean, like, we are looking at people who are more likely to get malaria, right? There is selection bias, but the bias exists at a group level, and the selection bias doesn't vary over time. What it means is that the presence of marshy land 6 months before the treatment is the same as the presence of marshy lands 6 months after the treatment. What it means is, as long as the selection level it exists at a group level and it doesn't vary over time, difference and difference will do its trick in such a way that these selection biases are cancelled out. But the key thing is, it should not vary over time. I can illustrate it by using an example here. So what it means is that, this is just a diagram I have, collated. So let's look at the graph on the left. So on the vertical axis, I'm measuring outcome, and on the horizontal axis, I'm measuring time. And this dashed line shows when the treatment happened. So if you look at the time before treatment, you see the outcome between the treated and the control population was progressing parallelly. And only after the treatment happened, the treated group started showing like a significant increase in their outcome, whereas the control group, didn't really show any significant increase in outcome. So the idea over here is that the two groups were progressing parallelly, although there is a selection bias which creates this systemic difference in y across the two groups before the treatment. it was sort of parallel before the treatment. And when parallel trends does not happen, the graph on the right. So you can see that before the treatment, there is something that is making these two groups sort of converge. So whatever is the selection bias which is causing the systemic difference between these two groups, they are changing over time. Over time, the selection bias is almost disappearing. So we cannot use the two-way fixed effect estimator on situations like the graph on the right. We can only cancel out selection biases that are time invariant using diff and diff. And how do we do that? Let me use this, simple example to demonstrate. Let us suppose I have an equation like this. Yit equals alpha I plus gamma t plus tau dit plus error. So this dit will take a value 1 if individual is in treatment group. It will take a value 0 if the individual is not in treatment group. Gamma t are all the factors that vary over time, and alpha I are all the factors that vary across the group or the individuals. Now we will measure two things: the expected Y in treated population before and after treatment, the expected value of Y in control population before and after treatment. So let us compute this from this equation. So before treatment means T equals 0, right? So this gamma T becomes gamma 0. And control population means D equals 0. So this thing goes out. And if I take expectation, then the error will also go out. So what I will have is alpha I plus gamma 0. Alpha I will stay alpha I because it is time invariant. Similarly, post-treatment for control population, I will have alpha I plus gamma 1. So 1 is post-treatment, 0 is pre-treatment. So this is my B, expected Y in control population before and after. And if you do the same for treated population, now this DI will be equal to 1 and we will have a tau factor. And if you look at, this B, this A, expected Y in treated group before and after, you will get expressions like this. So just simply post treatment, I'll get, tau 1, gamma 1 and alpha I. This one, same for pre-treatment. So this is my B. Now if I subtract A minus B, then the gammas will also get cancelled out and I'll get tau. And that is how the difference and difference measures impact of the treatment. And where is the selection bias? The selection bias is in alpha. So whatever is the difference across the individuals in treated and control population that is causing the selection bias, it's time invariant. It is in this alpha I. And this alpha I, because of the econometric design of the model, is getting cancelled out, which is why we can use difference and get rid of selection bias. And the last thing that I'll say about difference and difference is how do we evaluate it econometrically? We estimate an equation like this, and beta 3 is the impact of the treatment. In the interest of time, I'll be, fast. Beta 3 will have the same interpretation as that of a dummy variable that I explained before. So expected value of Y, pre minus post, expected value of in the treatment population, expected value of Y pre minus post in the control population. So this beta 3 is equivalent to the tau that we saw in this graph. So the beta 3 is the tau. Now, in the interest of time, let me move over to the other model that I'll be covering, that is propensity score matching. This is another very widely used causal model, and this is used in certain typical situation. So sometimes it is used in situation where the experiment has already happened. The exposure was not random exactly, but it's near random. So there is selection bias, but it's not a very strong selection bias. So for example, let's say a new variety of website was exposed to some customers. I don't know exactly how the customers were chosen, but I know that there wasn't really a proper criteria that was used to make this choice. And I have to evaluate, let's say, the CTR of that website. And I have, let's say, a wide variety of exploratory model, let's say some 500 exploratory variables that I can use to evaluate the impact of Y. So in these type of situations, propensity score modeling is used. And why is it used? That is because we have a dimensionality problem. We have a wide, that X vector that we talked about in a couple of slides ago, all the covariates that represents the selection bias. It's like a very long set of, metrics. So we have a big dimensionality problem here. So in these situations, score modeling is used. Another situation where it is used is where experimentation is not possible. For example, like, does smoking cause cancer? You can't really expect people to smoke more for your, experiment to get data for your experiment. No one will risk their life for your experiment. So in those situations, you have to use observational data, and you don't really know whether, certain type of people smoke or not. You could kind of assume that, it's sort of random, but you don't really know if, if the incidence of smoking is indeed truly random. So in those situations, you would use propensity score model. You have cross sectional data, and your observations are independent with each other, and these are all the assumptions that are required for a propensity score model. So, how does it really work? What it says is that I have a big dimensionality issue here, right? So, propensity score ideally tries to reduce the dimensionality problem. So, what it says is that if my yi0 and yi1, which is, the potential outcome before and after treatment, if it is independent of the treatment given the vector of x, then it is also independent of the treatment given a scalar function of all these x. That is the crux of the propensity score model. It is saying that instead of having this wide vector of, covariates to, take care of selection bias, I can take care of selection bias by using a scalar function of all these x's. So what they effectively do is that they compute a probability of getting treatment. They make selection bias represented by this number, probability of getting treatment. So they take all these x's and they compute like a logistic regression model, and every individual gets a score of how likely they were to receive the treatment. Now I also have, who are the treated population and who are the control population, right? So I use that score for the treated population, and let's say for one individual in the treated population I have a score of, let's say, 0.25. So then I try to find the exact same match from the control population or another individual who would have like a score around 0.25. Then I'll, compare those two individuals. So this is how mainly, propensity score works. And I mean, any kind of this matching algorithm work, and they use something like a KNN to do the matching. I'm not going into the detail. The purpose of this presentation is to, give you like a starting point to understand the underlying basic theory and intuition behind the causal models. And in the interest of time, I'll skip, instrumental variables. These are, like some resources that you could use if you want to, read more about A/B testing, difference and difference, propensity score matching, instrumental variables, Cupid. These are some common concepts that are, widely used in the causal literature. So this will, help you get started from, the basic starting point that I provided in this, lecture. And I hope that, this will give you enough motivation and enough groundwork to, get started. And that is the end of this lecture.
Thank you, Shreya. I appreciate you hosting this workshop. It was really informative. I do have some follow-up questions
Sure.
for audience to make sure that they understood all the materials. So, why is it important for us to think about the cause and effect instead of just looking at the patterns of data?
Sure, sure. So patterns of data, they are very sample or data specific. So data varies, right? Individuals vary across data. So if you make a conclusion by just looking at patterns in the data, then that same conclusion might not be valid in another data set because another data set can be different. And that is why not only a causal model, any model is very useful because the model would help you to come up with a generalizable pattern that might not be very obvious to the naked eye when somebody is just looking at slices and dices of data.
We talked a lot about experiments. Why is it important to think about situations where we can't run experiments, and how can we still trust the results of causal models?
So when random experiments are not possible, then there is always the risk of having a selection bias. So usually most people would be able to use their domain knowledge to and the overall industry knowledge to figure out if a selection bias is there. And if the selection bias is there, then as I said, whatever measure that you will get from doing a naive pre-post comparison, you will either grossly overestimate or underestimate the actual impact. So if you say that the impact is really large when the impact was, let's say, moderate to small, then it might happen that the leadership would, invest a lot more resources on, some initiative, thinking that this is really leading to an impact when in reality the impact was actually very small.
Okay. On that same thread, then, how do we make sure that our causal conclusions are fair and can work across different groups of people, especially in very diverse and global settings?
Sure, sure. Of course, that's a great question. So, usually, if I am a product manager, I would try to do like a random, like an A/B test, right? Because A/B test is like the gold standard. Now, if an A/B test for whatever reason is not possible, then I would try to do like some way of removing the selection bias. And there are some materials that I couldn't cover in this slide because of lack of time. Is that one needs to use the right causal model for the right situation. So that is very important. A significant amount of EDA or data analysis and data exploration needs to be done to even make sure that whether this is the right causal model to use for this exercise. So there are a laundry list of causal models available. I couldn't cover all. I covered only two, but one needs to be very very careful about their individual use cases, individual situations, data that they have, at what level the treatment was meted out, and they need to make sure that every causal model comes with a set of assumptions and with a set of restrictions, so the data satisfies those restrictions before blindly applying a causal model on the data.
Okay. Continuing on that thread, if two people see the same causal result, like in the treatment example that you were highlighting today, but one is technical, one is not technical. Our
Mhm.
viewers come from a lot of different backgrounds.
Sure.
How should the results be explained so that both of them can make an informed decision?
Sure, sure. So for a technical person, they need to only I would assume that they know all the assumptions that need to be valid for this, uh, for this causal experiment to be valid. So they need to, not only look at the beta coefficient estimate, they should, look at the standard errors. They should look at the confidence interval, make sure that, the confidence interval does not include zero. They need to look at the QPED estimates. If it's an A/B testing, they need to, look at a wide variety of, estimates. and then they can finally use that beta estimate to come up with a proper conclusion. Now if I'm dealing with a product manager or a non-technical person, then what the non-technical person needs to know is that how to interpret the beta, right? Let's take the salary example that I talked about. So another extra, like the beta one associated with that equation would be another extra year of education would increase my salary by beta one amount of dollars. And how stable is this estimate? uh, let's say if the p value was zero point zero 0.05, then I can say in 95% of the data. So if I do this on most of like many other data sets, 95% of the time I will see similar impact.
Yeah. And the last question for you, thank you for your time, is what should beginners in data science keep in mind when using causal models?
Know your undergraduate statistics very well. Know the very fundamental of the theory very well. Things that are often overlooked are variation, or what is really random, like what randomization truly means, how to like understand sample distribution, how to read standard errors, because standard errors are the bread and butter of any econometrician or a data analyst. You can get the coefficient estimate, you can look figure out if they're statistically significant or not, but figuring out the robustness of it or the standard error is very very important. If the standard error is low, then the coefficient estimates are robust. So I would advise all the junior data scientists out there is be very very cognizant of the standard errors of your estimates.
Great. Priya, thank you so much for your time and
Of
thank you for
course.
covering this super important topic. Thank you for everyone watching at home. This lecture will be live and for you to use to follow along and learn. Thank you so much again, Priya. You have a blessed weekend.